Hello, welcome to my presentation on the passive sign convention and power made easy. The first thing I'd like to discuss before we get into the details here of this short video is the passive sign convention. The passive sign convention is a very important technique used to assign voltage polarity across passive elements, whether they be resistors, capacitors, or inductors, when analyzing electric circuits. Using the passive sign convention is essential when writing either mesh loop equations or nodal equations. If you do not use this technique, you will most likely not be able to get the correct answer to the problem you are working. Therefore, you must get in the habit to always use this convention when analyzing circuits. Those of you that ignore the handout will most likely always have difficulty analyzing the circuit. That's something I always give my students in my circuits class. So let's begin by discussing what the passive sign convention is all about, and then we'll see how it's used in power calculation. There we have some circuits, and I repeated them here. There's a series circuit on the top left, and there's a parallel circuit on the top right. I don't care what direction you assign current. If you assign current through R1 in that direction, be sure to get in the habit of putting a plus on the left side where current enters and a negative sign on the right side. That's called the passive sign convention. Obviously, the current in a series circuit is going to continue, and the passive sign convention will show a positive at the top of R2 and a negative sign at the bottom. Current always enters the positive terminal of a passive element and it leaves on the negative terminal. That's because the passive elements have to exhibit voltage drops. There has to be a drop in voltage conventionally. Let's take a look at the parallel circuit. I don't care which way you assign the currents here. Let's say you assign it down. Always put a positive up there and a negative down there. You'll see why in the next couple whiteboards. If you assign the current here through R2 going down, put a positive sign there and put a negative sign there. Get in the habit when you analyze circuits if you draw a direction of current, you always have to accompany that arrow with a positive where the current enters and a negative where the current leaves the passive element. Down at the bottom, let's say you have current going this direction. You can do that. Put a positive down there and a negative up there. Obviously, in a series circuit, you can't change direction of current. It has to continue from right to left through R1. You put a positive on the right side and a negative on the left. That is the passive sign convention. Over here on the bottom right circuit, let's do the same thing there. Let's show the current going up there. And just for the heck of it, let's show the current going down here. Now, that can't happen because of the node voltages, but you'll just get a negative answer. You can assign direction any way you want. It's arbitrary. Put a positive down here as soon as you draw the arrow and a negative up there, and put a plus up here and put a negative down there. That is called the passive sign convention. It'll always work out for you. Let's continue on. Now, why am I stressing that so much? I don't want to do nodal analysis here, but I have another made easy presentation for nodal analysis. But let me show you the whole reason for that. Let's take a look at this circuit here. And obviously, if you put a ground down at this point, and most of the time you make the ground reference on the bottom, this whole wire here is ground. That's all the same point electrically. There's your ground point. That's your zero reference point. Zero voltage reference point. Don't call this up here V1. Don't call it Vx. That would be a dummy variable assignment because you know that's at 60 volts. There's 60 volts up there. It's a rise. Look at that. You're going from a negative and you're going more positive. You're going from the main floor of a house and you're stepping up in voltage. You're going toward the attic. So you're up 60 steps. In this case, you're up 60 volts up at the very top node up there. I don't care which way you assign currents. Any way you want, as long as you use the passive sign convention, the answer will work out fine. If the current comes out to be a negative value, you just assumed the wrong direction. That's how easy it is. So if you show a current going in that direction and call that I1, put a plus there and put a minus down here. If you show a current going in this direction here, through the 25 ohm resistor, make sure you put a plus there and a negative there. You're going to need that in your next step. I don't care which way you assign direction here, left to right and right to left. Let's go left to right. You better put a plus here and a negative there. That is the passive sign convention. And obviously that would be an unknown voltage there. We'll call that V1. And that would be an unknown voltage there. We'll call V2. There's only 2 unknown voltage nodes in that circuit. Now here's the next step. Again, this is nodal analysis, but I want to show you why the passive sign convention is very important, particularly in nodal analysis. And if you don't use it, you'll never get these problems right. If you take a look, and I call that current there IR, the voltage across the resistor R, okay? Or let's look at the current. The current across the resistor R, the current R through that resistor is going to be equal to, it's always the voltage on the positive side. That's where the passive sign convention comes in. It's the voltage on the positive side, which is V1, and you subtract the voltage on the negative side, which is V2, and you divide it by R. Well, that's just Ohm's law. There's current equal to current, and this is just Ohm's law over here. You see how that works? If we wanted to know what I1 is, look where I1 is in the circuit up there. It's the current through the 10 ohm resistor. It's the voltage on the plus side. You subtract the voltage on the negative side, and then you divide it by 10. That right there would be using the passive sign convention to calculate the current through the 10 ohm resistor. Voltage is always a subtraction problem. Remember that. For instance, if I say V total is equal to 60 volts in that circuit, well, it's with regard to reference. So when you see a single variable there, that VT right there, VT minus the reference via the ground reference. It's a subtraction problem. It's 60. In this case, you're subtracting 0, which is 60 volts. So even when those show a single letter designation as a subscript, it's still going to be a subtraction problem. You might be subtracting ground, but voltage is always a subtraction problem. Now, where does that come to play here to reinforce what I'm talking about? Well, right here. And again, I don't want to do nodal analysis. I just want to show you how incredibly easy it is to use a passive sign convention. Here's a ground reference right here. That's our ground reference. It's given. That's our 0 volts point. There's an unknown voltage. I'm going to call it V1. And here's an unknown voltage node right there. I'm going to call it V2. And you can assign currents. Let's just assign 2 currents. Let's assign a current there, and plus to minus. And let's assign a current going in that direction. We could went the other direction, but let's go in that direction. You put your plus to minus in. And then I'm going to label a current up here, even though we know it's 14 amps. I'm going to call that I1. I'm going to call this I2, and I'm going to call this I3. And I'm going to do a node equation. I'm going to say at node V1 by Kirchhoff's current law. That's nodal analysis. So I want you to just zero in on node V1 over here. That's all we're looking at. So my convention is currents coming in are positive and currents coming out of a node are negative. It makes more sense to me that way, although you can do it whatever convention. Some instructors like current going in is negative and current coming out is positive, but if you look at it in terms of water going into a bucket, water going into a bucket adds, water coming out of a bucket subtracts from the water in that bucket. So I like to look at conventional current flow that way. So if you do the top line equation, what you get is at node V1 by Kirchhoff's current law, you get a plus I1 because it's gone into the node, and you're going to get a minus I2 because it's leaving the node, and you're going to get a minus I3 because it's leaving the node, equals 0. That's a top level equation. Now look how easy it is to get the second equation. Don't try to go from the circuit to the second equation all the time. Get that first, put some currents in, and go to the second equation here after you write that top level equation. Just look at the circuit. I1 is given, it's 14. Subtract I2. Well, I2, if you take a look, it's the voltage on the plus side, it's V1, minus the voltage on the negative side, which is your ground reference, 0, divided by 4. What's I3? I3 is the voltage on the plus side, it's V1, minus V2, voltage on the negative side, so it's minus V2, and you're going to divide that by 5, and that's equal to 0. And you clean that up and you get one linear equation with two unknowns. When you're looking at node V2 by Kirchhoff's current law, top level equation, just zero in on node 2 now. You have to assign a current here, let's make it I4. Plus to minus now, this current, you know it goes in that direction, that'll be I5. The current source gives you the direction of the current, so it leaves, so it's I5. What's a top level equation? It's a plus I3 down here. Don't change it around. It's current going in. It's leaving node V1, but we're doing node V2. It's a plus I3 minus I4 minus I5 equals 0. I3, look at the circuit. It's the same magnitude as it was in the previous equation. It's V1 minus V2. It's the voltage on the plus side of the 5 ohm resistor. That's the left side. It's V1 minus V2, the voltage on the negative side, divided that by 5. The difference is it's a positive down there on the second equation. It was a negative magnitude. It was a negative value on the top equation. I4, look at I4. What is it? Minus I4, voltage on the plus side, which is V2, minus 0, which is voltage on the negative side, divide that by 5. Then you subtract I5, you're subtracting 7, equal to 0. There's your second equation. That's how important it is to use a passive sign convention. Now, let's take a look at power and see how you can use the passive sign convention on power. Power made easy. Look, here's a simple series circuit. And I want you to keep in mind, when you calculate power, power can be equal to voltage times the current. That's in watts. Or power can be equal to I squared R, and the units are watts. Or power can equal to voltage squared over R. This all comes from the Ohm's law, and that's equal watts. So when would you use the first equation? When would you use the second equation? When would you use the third equation? Well, the first equation when you know voltage and current. The second equation when you know current and resistance, and the last equation obviously is when you know the voltage and the resistance. So there's your three power equations. So let's see how the conventional sign convention helps you. The passive sign convention helps you. I'm going to make this 10 volts out here. I'm going to make that total voltage 10 volts just to make it something. I'm going to make this current here 5 ohms. So there's my circuit. Now I want you to take a look at conventional current there. I think you realize that the current flow in that circuit goes this way, it goes this way, it goes this way, it goes this way, and it comes up. It's a clockwise direction of current. And the current I, it's I total, it's the only current in that circuit, it's series. I total is equal to the total voltage, 10, divided by the total resistance, which is 5. Pretty easy. It's 2 amperes, but that's not what I wanted to show you. Anybody can do that in high school. That 2 amps, let's take a look at where it flows conventionally clockwise around the circuit. You know it puts a plus up here and it puts a minus down here. That's the passive sign convention. So let's look at what, if you look at that circuit, you absolutely know in that circuit that the voltage source has to supply power and the resistor has to absorb power and give it off in the form of heat. Resistors can never supply electrical power. Not going to happen. Resistors can only give it up in the form of that energy in the form of heat over time. Okay? So if you take a look at the passive sign convention, the power in that 5 ohm resistor, the equation I'm going to use, I know the current. I know the current's 2 amps in that circuit. And I know the resistance. So I'm going to use I squared R, which is equal to 4 squared. Okay. And I'm going to take that times, or 2 squared, I'm sorry, the current's 2. So I'm going to take that 2, square it, and I'm going to take it times R. Okay, you can see the power in the 5 ohm resistor is going to be equal to 4 times 5, which is 20 watts. But look, power is a vector quantity. It has to have 2 considerations to it. It has to have magnitude and direction in the sense of whether it's absorbing or supplying. There's 2 things involved with power. Some instructors make it a negative value and positive. That never made sense to me, trying to conventionalize it with a negative power and positive power. The best way to do this is say, if current enters the positive terminal of a device, if current enters the positive terminal of a device, which it does in the resistor, it has to be absorbing power. It has to absorb the power. And you know here that the power in the 10 volt has to be supplying. Well, we're going to use V times I on that. And the voltage there is 10. And the current in the circuit, we already said, was 2. That's your 20 watts. But take a look at what current's doing. It's going in. Look, the current enters the negative terminal of that device. So if current enters the negative terminal of a device or a device under test or a component, you know that component has to be supplying. That's a good way to look at that. So the reason I gave you this power made easy concept is when conventional current enters the negative terminal of a device, that device, no matter what it is, can't be a resistor, but that device is going to be supplying power. When current enters the plus terminal of a device, which could be a resistor, it's always absorbing. That's what I want you to get out of this. And then finally, let's see how it works. Because you may run into a situation that looks like this. This problem right here, we want to calculate the powers involved in that circuit. You want to take a look at that circuit, and you know there's going to be 3 power. There's going to be a power here, there's going to be a power involved there, and there's going to be a power involved there. Well, first of all, I want you to recognize something. That's a 4 amp current source that pushes conventional current in a counterclockwise direction, and you have that in the loop no matter what. That 4 amps is the boss. So that 4 amps has to flow in that direction, in this direction, in that direction. That 4 amps has to have a counterclockwise circulation to it in the entire circuit. Just like if this is a ground reference down here and that's 0 volts down there, there has to be 15 volts up there no matter what. The voltage gets fixed with a voltage source, but the current, that 15 volts has nothing to do with the current in that circuit. Just like that 4 amps has nothing to do with the voltage from there to there. So now that you know there's 4 amps in the circuit, let's go ahead and let's calculate some powers here, which are pretty interesting to calculate. If you take a look here, I can see that the current that's flowing counterclockwise in the circuit puts a voltage drop across this 3 ohm resistor. It's Ohm's law. It's 4. If you take a look, it's 4 amps times 3 ohms. So I think you'll see the 12 volts there. And keep in mind, plus to minus. There's that passive sign convention now. The current goes from right to left. So there's the voltage drop across that 3 ohm resistor. It's 4 amps times 3 is 12 volts, plus on the right, negative on the bottom, on the left side. So now let's calculate the power in the 15 volt source. And you say, what equation am I going to use there? What do I know? Do I know there's no resistance? So I'm going to use voltage because I know the voltage and I know the current. So if you look at that, the voltage is 15 volts. The current turns out to be equal to 4 amps. The product of that is 60 watts. But you're not done. That's only half the answer because it's a vector quantity here. So is the power in that 15 volt source being supplied to that circuit, or is it absorbing? Look at the current. The current is entering the positive terminal, just like it does a resistor. That has to be absorbing. That's absorbing power. Just because it's 15 volts, don't assume that it's always going to be supplying. It's absorbing. Take a look at the power in the 3 ohm resistor. Okay, the power in the 3 ohm resistor. We know the voltage, we know the resistance, but we can do an I squared R there. We can do an I squared R, so we know, let's do I squared R for that. So you have 4 squared. Okay, and you're going to take that times 3. Okay, 16 times 3. So you know it's 48 watts. Well, you know it's going to be absorbing. You could take a look and say, oh, the current's entering the positive terminal, but it always does on a resistor. Resistors always have to absorb. That's absorbing. What about the power in that 4 amp? The power in the 4 amp has to be the voltage across the 4 amp. Let's call it Vx. Let's put it up here and make it Vx. We have to find some voltage. That's the voltage across that 4 amp current source, Vx, times I. We know what I is going to be. So we have to find Vx. Well, let's see. Vx is equal to, I'm going to start at this ground point right here. I'm going to start at this ground point, which is 0. And I'm going to move around. It's really Kirchhoff's voltage law. But going around the loop, you go up 15, so you're up 15 volts. That puts you up here. Now we want to go over to Vx. And you're going up another 12. You're going to go up another 12. So you have 15 plus 12. Okay? That's going to equal 27 volts. Vx is, the point right here is 27 volts. Now you know the voltage across the current source. So now you can say the power in the 4 amp current source is equal to Vx times I, and you plug that in, 27 times 4, and you end up with 108 watts. 108 watts. But is that supplying or is that absorbing? Well, if that's 27 volts up here, now you know this point here, let's put it down here, that's plus 27 with respect to ground down here. So there's a plus up here and there's a minus down here. There's a positive voltage at the top of the current source and there's a negative relationship at the bottom. The current centering the negative side. That has to be supplying. And there's your answers. Absorbing, absorbing, and supplying. And always check your work, because the conservation of power says that the summation of the power supplied has to be equal to the summation of the power absorbed. So if you take a look at what's been supplied, you have 108, and that better equal the sum of the powers being absorbed, which is a 60 plus a 48, and you'll get 108 being supplied has to equal the 108 watts being absorbed, and you know you made your right calculations. So I hope that this video helped you understand how important the passive sign convention is, and how it helps you with nodal analysis and determining whether power gets absorbed or power gets supplied by a particular device. I hope you liked the video. If you did, your subscription to my channel would be greatly appreciated. Thanks.